We're going to go into the reactions of the aldehydes and ketones, and I'm going to expect you to be remembering the reactions that we learned last semester. So what I'm going to do in this online lecture is go over some of the old reactions, and hopefully you'll recall these. We'll go into the new reactions in another online lecture. Okay, we can oxidize alcohols to make aldehydes and ketones. We can use pyridine chlorochromate, which we call PCC, and if we have a primary alcohol, as shown right here, what do we get? We get an aldehyde, a primary alcohol, yes, gives me an aldehyde. A secondary alcohol will give me a ketone, and PCC will not oxidize these any further. So this is a nice gentle oxidation. There's another oxidizing agent we learned about, and that was chromic acid. When we have chromic acid, it will take a secondary alcohol and take it to a ketone just like PCC will. But when we have an aldehyde, so here's an aldehyde, or if we have a primary alcohol, as shown here, what happens is we oxidize all the way down to a carboxylic acid. Even it doesn't matter whether we use PCC or chromic acid for a secondary alcohol, but it does for a primary alcohol. A primary alcohol will be oxidized to a carboxylic acid with chromic acid, and you must use PCC if you want to stop at the aldehyde stage. And remember, an aldehyde will be oxidized by chromic acid just as if it were an alcohol, all the way down to a carboxylic acid. We can reduce aldehydes and ketones back to the alcohol that they may have come from with reduction of aldehydes and ketones can be done with either sodium borohydride or lithium aluminum hydride. Remember that we called sodium borohydride a gentle reducing agent, and it's fine for reducing both aldehydes and ketones down to the alcohol. However, lithium aluminum hydride is what we called a harsh reducing agent, and it will reduce both aldehydes and ketones to the alcohol, but it will also reduce other functional groups that have carbon oxygen double bonds in them, or carbon nitrogen double bonds, or even a carbon nitrogen triple bond. So if you have an aldehyde or a ketone and you're reducing it down to an alcohol, and there's other functional groups like esters or carboxylic acids or nitriles or nitro groups on there that you don't want reduced, you have to be careful. Lithium aluminum hydride will reduce them, and then you would want to choose sodium borohydride. Here we have a Grignard reaction. You can take this 2 away. That's a typo. I'm sorry. But here we have an aldehyde, but ketones work also. If you have a Grignard reagent, what will happen is this does nucleophilic attack on the carbonyl and makes an alcohol and adds the alkyl group to the carbonyl. We wash with water to protonate the oxygen afterwards. We can form hydrates of carbonyls. You can see that this is just having water added across the double bond. We put a hydrogen here, and down here we get an alcohol group. Notice we have a geminal diol on this carbon that used to have a double bond to an oxygen. The equilibrium is almost always favored to the carbonyl. There is an occasional hydrate that's formed in solution preferentially. For instance, when you replace the hydrogens with fluorines, then the hydrate is formed preferentially over the carbonyl. But for the majority of aldehydes and ketones, the hydrate would be present in solution in a very small quantity. Okay, all of the carbonyls will form a hydrate, but as I said, it's usually not favored. Notice that you can form the hydrate with either acid or base catalysis, and so the conditions are the same. The position of equilibrium is not determined by acid or base, but it's determined by the characteristics of the carbonyl compound. And it really is, almost all of them favor the carbonyl and not the hydrate. When we have either the Grignard reaction or the hydrate forms, what we're having is nucleophilic attack of the carbonyl. In nucleophilic attack, what happens, this has a negative charge on that carbon, and what does it do? It comes and attacks the carbonyl, and the negative charge jumps up onto the oxygen, which is then protonated with the acid wash. When we have hydration, you also have the carbonyl being attacked by either hydroxide in base catalyzed hydration or with water in acid catalyzed hydration. The reason I'm stressing this is that many of our other reactions that we're going to learn about in this chapter are based on nucleophilic addition. I want you to be very much aware that there is a large del positive on the carbonyl, and nucleophiles are attracted to them. When the nucleophile adds, this nucleophile comes in, adds to the carbon, and then the negative charge jumps up onto the oxygen, and we make an intermediate that has a nucleophile attached to the carbon, and then this oxygen, the alkoxide here, then which would be protonated by water or acid wash. Here's both of these are examples of this. Hydroxide coming into a carbonyl and making this tetrahedral intermediate. Or here's a Grignard reagent coming into a carbonyl and making this tetrahedral intermediate. Notice 4 bonds on the carbon. All nucleophilic attack on a carbonyl forms this tetrahedral intermediate. Notice 4 bonds on a carbon, tetrahedral intermediate from nucleophilic attack. So keep that in mind for the future. There are more nucleophilic carbonyl attacks that we're going to go through, but right now I want to make sure that you know how to practice these old reactions before we do the new. So the first thing that we're going to do is the hydrate of cyclohexanone, and then the product of butyl magnesium bromide with cyclohexanol. Then determine what is the product of chromic acid with 5-oxohexanal. And then what is one equivalent with sodium borohydride and 5-oxohexanal. And then I have another problem for you to do when we get through with these. But pause, and try to figure out what the answers to these would be, and restart the lecture. Okay, so what we're going to do is first the hydrate of cyclohexanone. Here is cyclohexanone. So the hydrate is formed by either acid catalysis or base catalysis in water. And what do we make? We make the geminal diol. What is the product of butyl magnesium bromide with cyclohexanone? Well, this is a Grignard reagent. Negative charge here does nucleophilic attack on the carbon in the carbonyl. We end up with an alcohol and an alkyl group on the carbon in the carbonyl. So what is the product of one equivalent of sodium borohydride with 5-oxohexanal? This is 5-oxohexanal, and you have got 2 functional groups that can be reduced. Which one will be reduced? The aldehyde is more reactive than the ketone, so the aldehyde will be reduced over the ketone. So what happens is we end up reducing the aldehyde to a primary alcohol. When we treat hexanal with methyl magnesium bromide, what happens? Well, first we get the addition of the methyl group, and we made an alcohol here, and then the chromic acid oxidizes that down to the ketone.